All right. So, yeah, thanks to Grand Circus, the Grand Rapids chapter, for bringing me in today. I'm really excited to talk to you all a little bit more about artificial intelligence and machine learning, and specifically why they matter, a few applications of them, as well as how can you get a start in working with these technologies. So, just brief way of introduction. I'm Andrew Hoekstra. I got my start in artificial intelligence by way of education. I went all the way up to the Upper Peninsula of Michigan to study electrical engineering at Michigan Tech. I got my master's degree up there in a particular niche called controls. And if you dive down even more, I focused in on optimal control. The reason why I bring that up is optimal control does essentially the same math that underlies most machine learning algorithms. If you were to go and study the underlying or inner workings of machine learning that today very few people have to be able to do. So it was just a really good introduction to that sort of math that helped me progress pretty quickly in my career to shift over to artificial intelligence instead of just simple controls. So currently I am the founder at Point Vector. It's a artificial intelligence and machine learning consultancy. And I'll go through a few projects that I've done through my career as sort of AI applications. But I got my start in the automotive industry working on autonomous vehicles. So that was my transition out of controls into AI. Controls is basically taking an input from AI saying, hey, you need to turn left here, and actually figuring out how to turn left. So pretty quickly I left that controls and got into AI. Lately I've been moving further and farther away from that hardcore engineering, working with circuits and microcontrollers and whatnot, and doing more of service industry stuff, which tends to be more business logic and forecasting sales or costs, and things of that nature. So bottom line is I help bold people pursue big ideas. That's what I'm all about, whether it's technologically focused or otherwise. So let's dive in. So why does artificial intelligence matter? Those who know me know I like to go on a lot of tangents, so bear with me on this one because I will bring it back around. One of my favorite bands is Vulfpeck, Vulfpeck. They have a song called Barbara where they overlay an interview that Steve Jobs had done, and he had brought up a research study in Scientific American by S.S. Wilson where they were studying the locomotive efficiency, so how efficient an animal can move across a wide variety of animals, and they found out that the condor was the most efficient, and humans came pretty close to dead last, until you consider that humans are tool builders. Once they considered that and they allowed a human to ride a bike and measure the efficiency, humans on a bike absolutely crushed the condor. So the concept there is we're tool builders, and that's basically where Steve Jobs got his line about making the bicycle of the mind, computers being the bicycle of the mind. So much like computers are a tool that we've built that enables the human race to be able to do so many more things, I like to call artificial intelligence the motorcycle of the mind, because it's a whole nother step beyond just working hard and pedaling on your bike. With the push of a button or the twist of a wrist, we're able to go even farther than we could with just compute capability being everywhere. So that's I also liken it to the internet of the 90s. So artificial intelligence, we're starting to see AI everywhere. And much like the internet in the 90s, we went from dial-up to high-speed internet very fast. So similarly, the artificial intelligence industry is developing at a rapid pace. Hype is really high, but the applications are actually real. They are somewhat limited to certain classes of problems and some niche things. But the important thing is that artificial intelligence and its development has all been about accessibility as of late. So if you look at the major cloud providers like Microsoft with Azure, Amazon with AWS, Google with Google Cloud, they're coming out with a whole bunch of auto machine learning applications where you pretty much just need to upload a data set and it'll help you create an endpoint that you can use a trained model that you don't need to really know any of the inner workings of to be able to use it. That's highly accessible. That's giving more and more people who have less and less technical skill the ability to do incredible things. So what does that mean for your career? The technology, fortunately, has not yet reached its prime. So what we're seeing in basically every industry is just an explosion of the capabilities of AI in every single direction. And there's a unique combination of an uncommon skill set to be able to do AI. But all the tools right now are quite accessible and becoming more and more accessible every year. So this is really kind of the forefront of being able to use AI in whatever industry you're interested in to do pretty much whatever applications. We're at this forefront where you're able to jump in at a really, really cool time. And the tools that you build today are going to shape mankind. Just like the computers shaped our ability to compute and automate things, AI is going to shape the way we interact with everybody and what business looks like, for better or worse. So I'm not seeing any questions, so I'm just going to also encourage once more that if anything pops up throughout any of this, please feel free to ask. We're going to start jumping into a little bit more technical depth and inspirational talk. So what is artificial intelligence versus machine learning? Because I've kind of been using both of those terms interchangeably. So by now you've probably viewed the image to the right here, where artificial intelligence is just a superset of machine learning. That's to say everything that is machine learning is also artificial intelligence, but not all artificial intelligence is machine learning. A lot of people like to draw the line in different ways. The way I typically draw the line between artificial intelligence and machine learning is understanding who's responsible for the feature engineering. So those unfamiliar with feature engineering, I'll use an example of face detection. So if I want to write computer software that can detect a face, the computer first has to understand features of the face. So it has to be able to identify an eye, has to be able to identify a nose, a mouth, maybe ears, maybe hair. And then it has to be able to use those features to recombine them and say, oh, now I can calculate the distance between eyes and how far away the nose is from the mouth. And then eventually we can combine up all this information and say there's a pretty high likelihood that this is actually a face in the image versus a tree or something that's not a face, right? So in machine learning, in artificial intelligence, there's an engineer sitting at a desk that's coming up with those features, deciding what those features are, how to detect them, and how to combine them. In machine learning, it's the computer that's deciding all those features. We're essentially just going to give the computer a whole bunch of data and we're going to label it as saying this has a face in it, this does not have a face in it. And the computer will come up with its own features that it learns. Maybe it gets more advanced and look at the way light hits the contours of my face. And that's a better feature for it. So who's responsible for defining those features is where I draw the line between artificial intelligence and machine learning. The truth is most practical applications actually use both. So machine learning has been the main driver behind a lot of the hype in the artificial intelligence space, because previously artificial intelligence was limited by a small amount of data. And with how much data we're getting from connected devices, we've been able to use very naive machine learning approaches that required a ridiculous amount of data to then learn how computers learn. And then we've been incrementally over the last decade making advances in making machine learning more efficient on smaller data sets or different data sets. So machine learning is responsible for a lot of the growth in AI, but AI is never going to go away or be completely consumed by machine learning, because machine learning often uses artificial intelligence to do its job better. So I won't go too much longer on this, but one example of that is machine learning. You have inputs, you have outputs, and it starts off by making random guesses of the output given an input. And then it compares the output to what you say is the expected output. And it uses those errors to update its internal model to make a slightly better prediction. And if you do that enough times, in theory, the computer will be able to make good predictions most, if not all the time. Now, somebody who's training up that machine learning algorithm has to decide how fast they want that internal workings to update. If you update too quickly, it might learn a very specific part of the data set and be very good at one part, but not good at another part. Or if you have it learn too slow, it might take you months to train up a model instead of weeks or days or however fast you want it to go. So there's a balance between, training fast and training well. And these auto machine learning applications that you see on the cloud providers, they do all of that tuning for you. So that tuning is actually using artificial intelligence to say what is an optimal way statistically to train models with different hyperparameters, they're called, the different tunings for how quickly to train, so that way we get the best results. So in almost every machine learning application at scale, you have some use of general artificial intelligence practices helping your machine learning work better. So yeah, that's kind of how I draw the line between AI and machine learning. So let's chat a little bit about some applications of machine learning. If you were to do a quick Google search out there, you would probably find a whole bunch of really common applications, such as taking an image and detecting people, cars, or bus stops or signs. There's also ones out there for detecting the different types of flowers. I'm going to try to avoid really common applications of it and use some real-world examples from projects that I've worked on over the last 6 or 7 years here. So starting off with the medical industry, this is actually one of my favorite applications, which is why I'm starting with it first, because my grandpa was an orthopedic surgeon doing back surgery, and we can actually use machine learning to get better surgical outcomes when performing back surgery. So a little bit of background. Patients and doctors want minimally invasive surgery. So instead of, hopefully this isn't too gruesome, opening up somebody's back so you can see everything that's going on and do a good surgery, the smaller of a cut and opening we have, the quicker patients heal and the better they heal. The problem is, without it being open wide up, there's no light source inside the body, so the doctors have a really hard time seeing what they're doing. And particularly with back surgery, being off by a millimeter or two could be the difference between a very successful surgery and the patient being paralyzed. So it's a really big deal and a really high stress environment for a doctor. So there's a lot of prep that goes into surgeries, and what we have here is an image of an intraoperative scan. So before the surgery, preoperative, they'll do a whole bunch of scans to be able to plan out the surgery, to see the inner workings of the body. But once you put the patient on the table, their body changes position and everything changes. So there's often, when the body's wide open, you can see how it changed. But when you're only looking through a tiny hole, they have to use medical imaging to see what's going on in the body. And in their minds, they have to match up what they saw preoperatively with what they're seeing during the operation. So the problem with this is the things that they can use to look during the surgery looks like images like this. So I'm feeling like I'm getting a little long-winded here, but if you look at the images here, these sort of dark bumps that you see on each of the image are actually bone, so the spine. And then at the very top of the image, this light curve would be the skin surface. So we're kind of getting a cross-sectional view into the body. Now the tricky part is where you see the edge, the boundary of the bone, that dark bump, that's not actually where the surface is in the image. It looks like it is, but unfortunately, with the way the physics of the sensor works, the boundary is in a slightly different place. So we're using algorithms to try to detect where the actual boundary of the bone is, and that's really important because, again, being off by a millimeter or two could be paralysis. So it's really important to understand that bone surface. So yeah, we're basically, I like to think of it as, in CSI or those other shows where they take some crazy blurred image and make it super highly resolution where you can read the license plate. That's essentially what we're doing here for doctors, is giving them superpowers and being able to see where the true bone surface is. And that way in the back end, we can match that up with the preoperative information. So that way they can do a successful surgery, or in the long run, maybe even a robot can do the surgery. So yeah, that's one potential application within the medical industry. It's basically using computer vision on non-camera applications, but medical images to be able to give doctors superpowers and see surfaces that are kind of hidden within the image to be able to do better surgery. Another application would be in the transportation industry, which, as I said towards the beginning of the presentation, is where I got my start. We can use machine learning in a couple of different ways to make railroads safer. So I don't think there's really anybody out there that wants a train to derail. Most of the time when we hear about that in the news, it's a passenger rail. But what's interesting is most of the railroad trips in the United States, the commerce around it, is actually in freight. And freight is getting heavier, trains are getting faster, and we're trying to send more and more trains over the same track, which freight does a number, like it destroys track way quicker than passenger trains. So it's really important that we inspect every single foot of track very, very frequently for safety and performance, because the rail profile, which you can see here in the image, the outline of the rail actually wears down over time. And to keep the train on the track, the geometry between the two rails, whether one's slightly higher than the other, or they're tilted in or out from each other, is extremely important. So they used to have people who would go out on track and physically measure that. But we've reached a scale and a level of sophistication that that's just no longer practical. So one of the applications that we use is using a laser to essentially measure the distance of the surface of that rail from the device and generate a number of points that we then can say, what rail do we what's the characteristics of the rail that we're dealing with at this particular foot. So we can automate the collection of that data, so a person doesn't necessarily have to go out and measure that anymore, which is a lot more error prone as well. So there's one additional piece that's really important to know for context. There's not just one rail type out there. There's a ton of different rail types, and railroads don't know what rail they have where, and not all rail is compatible with each other. So you can't just drop in rail wherever you feel like. So the very first thing after collecting points along the rail is we need to use machine learning to detect the rail type. But it's very noisy because the surface is worn down. So we have to be able to take this dirty data, if you will, and say, is this 136 pound rail or is this 160 RE pound rail? It would take us forever to do that for every single foot of rail in the United States. So the only practical way to do that is to use machine learning to have it learn from points what type of rail we're dealing with. Once we understand the type of rail, then we can do all kinds of really cool things. We can take that rail geometry, that profile, and do measurements like the cant of the rail, how much it's tilted in. We can relate the two pieces of rail to each other to see how much one's elevated over the other. And all of that geometry can be captured. And we can use that to kind of calculate a health of the rail. And that health is really important because if we take that data over time by measuring the same sections of rail over and over, we can actually generate a forecast for the Class 1 railroads to say, you're probably going to need to replace these sections of rail within the next year or 5 years or what have you. And that is a huge value proposition to them that they spend a ton of money on. Because first of all, they don't even know what rail they have out there. So being able to tell them that is good. But being able to tell them when they need to replace it keeps our tracks safe and keeps your Amazon packages on time, which I think everybody would agree is a very, very good and wonderful thing. So going to applications that are a little bit more recent in my work history, we can also use machine learning for industries that I would say typically aren't the first thought for artificial intelligence applications. So we can actually use machine learning to help individual restaurants figure out what the best equipment for them to have in their kitchen, what that equipment is. Because part of the problem that if you've ever worked in the food service industry or managed a kitchen or maybe even owned your own restaurant, I don't know, is the preparation equipment breaks down all the time. And whenever it breaks down, unless you've got a redundant piece of equipment, you can't serve that food, and that makes your ratings go bad. So this is a huge problem, and they often have to decide, is this the time to repair the equipment, or is it cheaper or faster for me to just replace the equipment? Unfortunately, there's a lot of turnover in staff in the restaurant industry, so kind of this industry knowledge of when to make that ideal trade-off isn't always captured. So I was working with a group that had a whole bunch of invoices for restaurants across the United States. And we could look at the historical trends and look at the equipment type, the location, the type of problem, and be able to get a good estimate on how much a repair might cost in the future, and maybe even when a repair might happen. And if you take that history over a whole bunch of different equipment across a whole bunch of different restaurants, you can actually understand how each brand and model of equipment, what its total cost of ownership looks like. So now you can start to provide information to restaurants saying, hey, you've already spent, 95% of the expected total cost of this equipment, and it's probably going to break down soon and be really expensive. You're best off just replacing this. You got your use out of this equipment, just get it replaced quickly, and that's going to be the better decision for you than trying to get it repaired yet again when it's probably going to break down next month. So yeah, this is a really, really great application. And one of the reasons why I wanted to target this one is because it's also a fantastic application of AutoML. So this is one where we didn't have to do custom modeling and a whole bunch of programming to figure out how do we represent the solution to this problem. We literally just collected all of this data. We had to use, we used an online service, Amazon's Textract, to do optical character recognition to be able to extract information out of the invoices So that way we were able to populate the cost, the location where the equipment was, what the equipment was, and all of that sort of good stuff. But all we had to do then was put all the information in a giant CSV, upload it to Amazon's AutoML, and through a little bit of feature engineering where we kind of guided it towards the right solution, it came up with the model for us that we could deploy and start using. And within 2 weeks from the start of the project, we were able to have a solution up and running for the service providers, which is incredible pace based on my experience from previous projects of applying AI. So whenever you have structured data like that, where if you think of like a database where there's rows and columns, that's usually a really good sign if you're wanting to predict the value in a particular column for if you have the values of the other columns. That sort of structured data is a great opportunity to save yourself a lot of time and do some really cool things without hardly breaking a sweat by using some of these online services. It is quite easy, but there's also a number of things that once you get into it, you'll find out there's a lot of gotchas and a lot of things that make this problem also really fun to deal with. So we'll talk a little bit more about that in a moment. I've got one more application for you. I didn't know how many to put, how many I would bore you with, but my goal here is to kind of show you a wide variety of industries and a couple of different uses of technology to hopefully spark some ideas beyond just tutorials that you can find online. So this last one is with car dealerships. So it's sort of a classic application where it helps a business be more effective if it knows what future sales might look like. And the reason why this is particularly important in the automotive dealership industry is that they operate in a very, very complex system where they're negotiating deals, but they're also taking trade-ins, and they don't know what those trade-in vehicles are going to be that they have to figure out how to get rid of profitably or at least at cost. And the dealerships also have a whole bunch of different incentives that makes them want to time their sales at certain times to maximize their incentives. But they also don't always get to choose every single car that gets put on their lot that comes from the dealership. So they've got a lot of constraints that they have to deal with, and they often can't predict sales. So they really just are making a whole bunch of decisions from intuition. And machine learning can take all of this data that is readily available but really hard to process and give some data behind their intuition, which helps them make better and, I think, most importantly, consistent decisions as opposed to just going by gut feel. So how this essentially works is particularly interesting. In the automotive industry, I don't know the last time you may have gone and searched for a used or new vehicle, but other than the dealership's webpage, there is all sorts of sources for finding these vehicles that are available to be purchased. And so the group I was working with actually used web scraping to collect a whole bunch of this data and organize it, dedupe it, and all this type of stuff to make it available. And then they also work with the dealerships to collect Google and Facebook analytics to be able to get website data and marketing campaigns. So there's this whole treasure trove of data, which is almost, too much to fathom how you could possibly use it all. And so the problem is, how do you find those golden nuggets? How do you work with the dealership to understand their needs and what decisions they need to make so you can find the right data in this sea of information and, of course, clean it up because it's very messy coming from web scraped info. And not only just give them a dashboard that's saying, hey, here's your predicted sales, but to be able to say, here are the actions that you can take to improve these areas. I think a lot of times when people talk about forecasting with artificial intelligence, it only gets to like the dashboard stage where people are saying, hey, we took all this information, we summarized it, and gave you really great insights. But businesses often struggle when they try to apply machine learning at first because they're going for insights as opposed to going for actionable outcomes. And unfortunately, that makes the problem of applying machine learning that much more difficult, because it's not just about being in your cubicle or your working from home space and crunching numbers on a computer and geeking out the whole time, which is a lot of fun. But you actually have to go and interact with people and figure out, like, it's not just talking with people, it's actually trying to dive down to their true needs, not just the symptoms that they're saying. So it's a very human-centered design sort of approach of figuring out what actions are they trying to figure out that they need to take, to figure out what data they need, to then go to the data you have and figure out how to create the insights they need to make those actions. So yeah, it's just a really interesting application in the automotive industry, but I thought it'd be a good way to kind of highlight that process a little bit more. So getting past applications and diving into how do you get a start in machine learning. The number one thing, first thing on the slide here, study Python. Technically that's an opinion, but I'd say it's barely an opinion, because most opportunities that you have to apply machine learning use Python under the hood, whether it's TensorFlow, PyTorch, or other frameworks, or if you're using a managed web service like Azure, AWS, yeah, they've got JavaScript interfaces and all of that. But even if you're looking through toy examples online, or help tickets and stuff like that, like, everything's going to have Python on it, because most people do machine learning in Python. It's just going to behoove you to not just know how to do it, but also kind of master it, become an expert in it. One caveat that I have to that is if you're doing a lot of embedded applications where you're using microcontrollers or trying to put something on a limited end device, C and C++ is also really important. But you're not going to do all your prototyping in C or C++. You're probably going to do some data analysis first on a beefier computer, and chances are you're going to do it in Python because it's just way more productive. So very first thing, master Python, because it will be your best friend in all of this. How do you do that? I'm not going to give a whole bunch of resources because it's as easy as a Google search. There's so many tutorials and classes through things like Udemy or Coursera online. But the one piece of advice I will give you on that is, if you need sort of like a guiding focus to direct your studies, I would look at web scraping as an application to learn Python. The reason for that is you need data to feed models, and there is so much information available on the web that makes the problem unique. If you only follow tutorials, that's really great for getting the concepts down, but until you throw data that isn't all prepared for you at it, you're not going to run into the same kind of problems that you're going to run into in the real world. And that's where all of the really important learnings are. Yes. So the second thing, once you've become a Python master, I would very quickly, even before you're a master in Python, start getting exposure to TensorFlow or PyTorch or what have you. I put TensorFlow first because I believe it was first, and it's the thing that I'm most comfortable with. TensorFlow is made by Google. PyTorch, the other, probably the second most used one, is primarily by Facebook. This is really helpful for when you go beyond sort of the managed services that cloud providers offer, like the AutoML applications. Those are really great for getting a good start. They provide a lot of value very, very fast. But there's always going to be applications that you just can't upload to the cloud and have somebody else solve for you, essentially. And so once you need to start doing custom things or adapting existing solutions to fit your particular problem, you're going to be in these frameworks, and you're going to want to have some practice in them so that way you can be efficient with it. Yes. So one question that just popped up, how heavy on math usage is machine learning / AI development? Basic algebra, statistics, calculus, deeper yet? It's a really good question. It kind of depends on what type of AI you want to do. As I said towards the beginning of the presentation, I view this a lot like the internet in that the tools are becoming more and more accessible. So every single year, you need less and less math to be able to do more and more things. If you want to study, the architectures that are being used and like innovate a completely new architecture that's going to blow everything else out of the water, you probably want to know calculus, and you want to understand what you're doing and why, because that's going to guide your architecture development. But very few people have a need to do that in the applications that businesses need right now. Also, like I was saying earlier, a lot of businesses are struggling to apply AI to begin with, simply because they're going after low-hanging fruit, and they haven't had to have a good practice with data. So a lot of the applications, the low-hanging fruit out there, don't require anything beyond statistics or just basic math and algebra. So I would keep it. I wouldn't say anything more than the statistics, because you need to understand the contents of your data set to know when it's imbalanced. Like if you have a whole bunch of examples of one thing and hardly any examples of another, that's going to introduce a lot of bias into your model. But you also need to know performance metrics, right? So when you start to look at what it predicted versus what it should have predicted, you got to be able to understand things like root mean square error. So what is root mean square error? How is it calculated? And if I see that value go up versus mean absolute error, what does that mean? And which one? You often, when you train a machine learning algorithm, you have to pick one of those for it to optimize on. And so just understanding enough of the math to understand which one to choose will get you a long way. But you also can develop an intuition for that if you don't have that math. So I'm not saying if you don't understand that basic algebra and statistics, you can't even get a start in it. You're just going to have a more lengthy process of getting an intuitive feel of which metrics are more successful for your problem or application than others. So hopefully I answered that question pretty well. If not, shoot me another one. Right. So TensorFlow, Python based. One of the reasons why I kind of emphasize TensorFlow a little bit more as a practical skill to come up on that tool set is they offer a certification, which I do not yet have. Haven't had a need to get it yet. But that certification, even if you don't go and formally get that certification, they have a lot of resources, and the things that they want you to learn to get that certification is a really great way to guide yourself in getting a wide exposure to make yourself a generalist in AI. If you're not really sure what industry you want to work in or what sorts of technologies within AI you want to get involved with, that's a really good way to kind of guide your studies, to just look through their certification program and try to see if you might be able to pass that, whether you actually take it or not. If you do decide to take it, they do have scholarships available if you need some financial assistance with that. So even more than just making the technology accessible, they're also trying to make the education on it accessible, which I think is a fantastic thing. Also, this is maybe not the normal recommendation coming from a machine learning engineer, but if you want to get a start in machine learning, I am of the strong opinion that you need to get yourself on LinkedIn if you aren't already. I got a number of reasons for that. First of all, there's a ton of people on LinkedIn who are experimenting with AI in personal projects. There's groups for artificial intelligence and machine learning where people are putting up papers. Even if you don't fully understand all the math that's going on in the paper, it gives you kind of a good pulse on what's happening in the industry. But there are personal projects that people are discussing. They're presenting the challenges they face when they're in the industry. Getting exposure to that sort of information flowing around can help so much to give you context while you're studying how to, or you're practicing how to apply machine learning things. Because it just takes time to develop, pretty much in any industry, kind of the best practices and to avoid pitfalls. And if you can learn from other people, it always helps. And LinkedIn's particularly good for that as opposed to Facebook or Instagram. Also, for my agency Point Vector, I've actually won all of my business for that company on LinkedIn. So that, if that gives you any indication at all, there are people on LinkedIn looking for not just people who can do machine learning, but people who can learn to do machine learning, or are even just trying to apply machine learning. It's quite incredible how just posting what you're doing, working out loud, if you will, online with the things that you're trying or succeeding in or even failing in, can generate a lot of conversation and get you connected to potential employers who are actively looking to fill skill gaps, where they're trying to bring this technology in-house. So whatever you're doing to study Python and TensorFlow or whatever framework you choose, put that stuff on LinkedIn. Just work out loud and be part of the community, because it's going to pay dividends in the long run. And I kind of alluded to this earlier in the presentation, but I want to make it really, really explicit. You got to get your hands dirty. So you got to get your hands on this dirty data. If you just simply follow tutorials online, the data is so well packaged up in most cases that you'll learn concepts. But I would tell you that the most time I spend actually applying machine learning in the industry is actually spent looking at the data set and preparing the data set and cleaning the data set and just understanding it and dealing with its limitations. Most of my time is spent on that instead of going, oh, cool, look at all the really cool insights and actions I can give you. Most of the time is spent there. So some of the things to think about when you're looking at your data set, the reason why it's really important to be spending a lot of time on your data set is a lot of people talk about the 4 V's of your data. That's volume, velocity, variety, and veracity. I think they just forced them all to be V's. They could have used much clearer words. So volume would be, how much data do I have? Some algorithms require a lot. Some you don't hardly need any whatsoever. And it's going to take some time practicing and understanding the contents of your data set to know how much you actually need. So the other thing is velocity. How quickly is your data set changing? Are you getting a ton of data in all the time, or are you working with a static data set that's just never changing because you have to deploy something that won't ever be updated, which is semi-rare. But the last two, I think, are probably the most important reasons why you need to spend a lot of time looking at your data set when you're doing machine learning, and that's variety and veracity. Variety, there's more and more research papers out there that are saying that algorithms don't necessarily need as much data as we think they do. What's more important is they need as much variety as possible. So to go back to the example I used earlier with facial detection in an image, if all I have are a bunch of images of a face straight on, like you see here in the Zoom call, that's going to be all you're going to be able to detect. If I did it without glasses on and nobody had glasses and I put glasses on, or even worse, sunglasses, now I can't detect eyes, right? If you have enough variation where people have their heads turned, maybe they're upside down, maybe their face is partially occluded, that sort of variety in the data set is going to help the machine learning algorithm perform better, not just in those edge cases, if you will, but it's going to force the algorithm to not just get into neat little tricks, like looking at a particular spot in the image for an eye, because it learned if it does that, it does really well. It forces the algorithm to generalize a lot more and actually understand, okay, what does actually constitute a face, as opposed to I'm going to look for an eye here and here in the image, and if I don't see it, then it's not a face. So the last one is veracity. And that gets to this getting your hands into dirty data. A lot of people will take data at face value and just run it through an algorithm and make business decisions off of it. And sometimes that can work for a month or two, and businesses get all excited that their machine learning algorithm is doing wonderful things for their business. And then it stops working. Maybe somebody who is entering in the data that it relied on, they have a different person doing it and they're entering it in differently or doing it wrong. Who knows? There's a whole bunch of reasons why you might not actually be able to trust the data that you're putting into the model. And so even after you've deployed a working model, you have to be consistently looking back at the data set and consistently updating your model over time, because one, the model is going to drift in its performance as the data changes, but you also have to keep making sure that you can trust the data that comes in, that you're processing and using to train up that model. So all of this to say, in a very long-winded way, please do more than just a whole bunch of tutorials online. I'd encourage you to use Python, do a bunch of web scraping to grab information that doesn't yet exist as a collected data set, and figure out the pains of dealing with missing data, wrong data, incomplete data, poorly formatted data, and figure out how to wrangle that into a usable state to make something. Because even if your algorithm just performs okay compared to like a canned data set that you can get to perform really well, you're going to learn a whole lot more messing around with that dirty data than just following a tutorial. So, yes, that is all I have for you today. Hopefully that spurred maybe some inspiration, maybe some questions, but we've got a little bit more time here that I can take a few more questions if anybody's interested in diving deeper into a topic or two. Do you have any questions? Yes. Yeah, don't have to type them in. Yeah, so sort of like an adversarial attack, right? So it yes, absolutely. So that really good example of that would be in the automotive industry with self-driving vehicles, right? It's a very high concern of the automotive industry that they protect the algorithms that they develop that detect people, other vehicles in front of them, that somebody can't just like tape on a specially designed image that says there's no vehicle here and have the vehicle crash, right? Like you can imagine somebody who wants somebody to get in an accident and just like start taping up things or like reroute them somewhere by saying the road doesn't exist in front of you. It actually goes to the left here. There's toy examples of people being able to do that. And it's actually an area of study where people are trying to make very successful algorithms to generate those sorts of adversarial attacks. And that actually spawned off a whole research area of study where they've come up with a new architecture called generative adversarial networks. So they essentially have two networks where one is trying to do the right thing and come up with good answers, and the other algorithm is learning to try to like fool that first algorithm to mess up. And so you're training kind of both of these things to kind of compete with each other. And if you do it the right way, you can get a very robust system. And there's actually some really cool applications of this. I'd encourage you to check out. I'll put the link in the Zoom chat here, but it's called thispersondoesnotexist.com. Didn't make a hyperlink. Crap. Anyway, it's really cool because they've used this generative adversarial network to come up with realistic faces by inputting just noise in the inputs. So by changing to random noise, you can automatically generate brand new realistic faces every time you hit refresh on that website. So none of the faces you see on there are real people. They're just completely made up images, which I think is such an incredible application of AI in that besides just solving business problems, this is an opportunity for artists to do very interesting things, right? So if you're interested in things like I'm very inspired by this painter and this painter, but I want to capture this subject matter here, right? Like I want to make my architecture a picture of this house that I've designed in my architecture class look like Van Gogh's work. There's a way you can train up a generative adversarial network to input your image of your architectural house, and it will actually paint it like Van Gogh's style. So it can learn Van Gogh's style. Google also put out WaveNet where it can generate new melodies and tunes, and it can also transfer the style of music. So you could give it a rock song and have it play it like it's a classical song. So this gives artists the opportunities to start like mixing and matching and playing with combining different ideas and creating something completely new. Even if the output of the algorithm isn't the product, that process of experimentation can happen so much faster that enables a lot of creativity. So long-winded answer to your adversarial stuff, but hopefully it was a good path to travel down. Any? Yeah. 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 So please feel free to connect with me on LinkedIn. Yeah, I'd love to pass along some info for groups that you can be part of on LinkedIn that are talking about AI and machine learning all the time. Excuse me. And yeah, there's plenty of thought leaders too that I can also recommend you reach out to. So here's another question that came in. Excuse me, I'm going to grab a drink of water real quick. Any good encryption techniques? So I'm not entirely certain the direction you wanted me to answer this question in terms of like how to apply encryption with machine learning. So if you pass me another question to clarify that, I'll start talking about a few things that I think might be relevant, but if I'm not hitting them, just send me another one. So one of the concerns with machine learning is that you often have to use cloud compute for it. And that means you have to upload potentially very sensitive data. to the cloud. And so you want to be able to encrypt that data, but it's very difficult to have a machine learn encrypted data if it can't understand the encrypted data. And if you're deploying a model and people can hit that model with an endpoint, they might be able to understand some things that are happening internally just by hitting it with data. So there is research into having machine learning models do I think it's like holographic techniques, where essentially you can pass in encrypted information and the machine learning algorithm is actually able to learn on encrypted information, where it's really interesting. It doesn't understand what it's learning, but it can learn regardless. So it doesn't even know what the input data is or the outputs that it's recommending. So there's no way for anybody, if they even captured the model, like stole it from your server or something, that they could reverse engineer and redeploy it their own way. They'd have to understand the full end-to-end encryption of it. That's still very much in the early phases. So very tough problem. That one you'd probably need a little bit more math for. If you were talking about encryption techniques for using machine learning to make better encryption techniques, I am personally not very aware of that, partially because I haven't looked for it, but I would have to believe that the security community would be very wary of machine learned algorithms because they can be somewhat black box. Not all models, or very few models, are actually explainable, like how it comes up with the outputs from the inputs. And encryption has to be able to be like fully dissected and understood and proved to be correct before anybody's going to be willing to put trust in it. There are a lot of compression techniques from machine learning, but that wasn't asked, so we can go into that if anyone's interested. Another question coming in is, where's a good website or book to start looking for Python and AI tutorials if you're just getting started? So I got into machine learning and AI early, and not from the Python perspective, and I just kind of learned Python along the way. So I essentially learned it on the job. But I would say my best recommendation for getting into this would be to take a look at Tensorflow's certification program. Even if you don't actually do the program, they have I think it's a Coursera course that they recommend on there. I probably should have had that ready for this presentation, but if you just do a Google search for TensorFlow and their certification program, they've got a whole list of resources there that'll help you find good tutorials to get into this. And again, they require a wide breadth of experience to be able to pass that certification. Not necessarily a long time doing it, but they cover a lot of ground, a lot of different techniques. So it's a really, really good way to sort of understand how much of the scope of AI you've given yourself exposure to, and maybe to give you some keywords to be able to search and find good tutorials. If you're interested, I can, if we're connected on LinkedIn or otherwise, get connected otherwise, I can make sure to collect some of those resources as links and send them out to you.